Differential equations are everywhere. They have been used to describe weather and climate phenomena and the transportation of pollution in the atmosphere. They've been used to model plankton and nutrients in the sea and the spread of diseases. Unsurprisingly, the computation of numerical solutions to differential equations has long been an important branch of mathematics. When modelling complex physical phenomena on a computer, geometry and symmetries are often important as they are the mathematical manifestation of the underlying laws of physics. Yet, historically, this fact has been ignored when creating numerical approximations to differential equations. But recently, this has changed. Focus has shifted to considering purpose-built algorithms that preserve key structural properties of the specific problems under study. Such methods are called structure-preserving integrators. This approach can lead to better and faster numerical approximations. The CHiPS project addresses fundamental questions regarding structure-preserving algorithms.
The philosophy behind our research is simple. All physical laws have a geometric foundation. We want to create numerical methods that preserve these geometric properties and invariants. The goal is the faster and accurate computation of numerical solutions.
The practical applications for these new mathematical methods are numerous and diverse.
So the fun of the research we do is that we get to solve differential equations. Why is that fun? Because differential equations, they are behind the laws of nature. So in order to understand nature, we need to be able to solve these equations. And if the differential equation evolves on a flat manifold, then we have very good methods for solving these equations on a computer. But if they evolved on curved manifolds, then it's more complicated and you need to take geometry into account. And one particular system that I like to investigate are so-called spin systems in physics. And these systems, they evolved on curved surfaces. And in order to be able to solve these systems and still retain the physical relevance, we need to understand the geometry of these curved spaces.
In the last 15 years, engineers and physicists found a way of controlling the behavior of single particles using rapid laser bursts. And this is the probable pathway, for example, toward construction of quantum computers. However, the equations involved in this are fiendishly complicated. They exhibit very rapid oscillation at several levels, and they have plenty of important structure that needs to be conserved under discretization. And hence this represents a very difficult challenge.
The type of applications that arise in this context come from medical imaging, from biology, from remote sensing, from seismology, from art restoration. So very often there are structures in images that these mathematical methods are exploiting, are modeling in order to extract information from these images. And these structures either come from some physical process that you know that the image has been going through before you observe it, or there are some geometric properties that you know the image has and that are very characteristic to these images.
So in the project we were interested in mainly applications from computer graphics and computer animation, but there are many applications of these techniques where you all need structure preservation. So for example, you can do hurricane tracking or bird migration. There's an underlying structure to this data you want to analyze and want to manipulate. And all the methods you develop should respect this underlying structure. And this is where abstract infinite dimensional theory is coming in. This is for all people involved quite surprising because the practitioners come from a very applied problem that they want to look at, for example, movements of characters in a computer game. From the outset you think, how hard can it be? And then it turns out that you want to do infinite dimensional geometric methods to really understand how you preserve the structures.
So it's something we see all over in mathematics, that certain structures turn out to appear in many different contexts. And in particular, perhaps the most simple structures, they are the most universal, and they describe something fundamental that is commonplace in many areas of mathematics. And the surprising thing about these structures that we are discussing here is that they have not been discovered before. They are new in the last decade or so, and Our motivation was computational mathematics, but they turned out to be popping up in all other contexts, in differential geometry and in stochastics and control theory. So it's a rather surprising phenomenon. And I think that the role of computation is rather striking. That computational mathematics is in the central part of mathematics, because this is binding together various areas of mathematics in a very nice manner. So the role of focusing of computation turned out to be a sort of a glue pulling together various areas of mathematics. That is very exciting.
Abstraction and application go hand in hand. While the goal of the CHiPS project is computation, we also seek to solve the theoretical challenges that arise along the way. In doing so, we will gain a deeper understanding of practical problems, possibly resulting in better solutions. But mathematics doesn't end where computation begins. Our project is only really successful if the results are helpful to others outside the mathematical community. One of the main goals of our project is to make sure that our innovative processes are implemented in usable software tools. With the CHiPS project, we want to develop new mathematics and fast numerical methods, and we want these methods to be used in everyday life.